All right. Hey, everybody. So we're going to be doing statistical inference and binomial distribution for the next assignment. First up, welcome back. I hope testing and spring break went well. Sorry I'm getting on this late. It's been kind of a crazy week. After I upload this, it may be tomorrow, but I'm going to do my best to do it today. I'll be uploading a lecture specifically on standard deviation, and I'll be putting up an assignment due in 2 weeks. You'll still have the quiz that's due on this in a week and change. I'll give you some extra days, probably until end of next Sunday, but that one will be due in 2 weeks. The standard deviation assignment's going to be extra credit. Hopefully, you'll get some understanding of kind of a little bit more detail of what is standard deviation and how we use it. But let's jump in. So first, some definitions. We've talked about this some already, but kind of jumping in fully now. The first one we talk about is the population. So the population is the overall group of people that the research question is focusing on. Let's say I do a study on 500 American seniors over the age of 65 to see, how vulnerable they are to the flu. My population is going to be Americans over the age of 65. So everybody that research is designed to apply to. Our parameter is kind of a fixed number that describes the population. I know that's vague. So a good example, this is going to be like a specific number, what we're studying, how many hours of sleep does this population get per night? How many hours do they spend studying? What percentage is left-handed? Things like that. Those would be parameters when we're referring to a population. Next, sample. So that's the group of people that we're directly studying. Who we're doing the research on is the sample. And then statistic is basically the parameter, but for the sample. It's the exact same info, but it's from this specific study that you did. So let's say if we studied Americans over 65, how many hours of sleep they get a night. If we studied, let's say, 500 people over the age of 65, and we find that they sleep 7 hours a night, that would mean that our statistic is 7 hours of sleep per night. Easy way to remember this is the P's go with P's and the S's go with S's. Population parameter, sample statistic. So an example that we'll work through here from the book I'm using. Since 1997, Student Monitor has published an annual market research study that provides clients with information about the college student market. The firm uses a random sample of 1,200 students located throughout the United States. One phase of the research focuses on lifestyle and media. The firm reports that the undergraduates spend an average of 15.1 hours weekly on schoolwork outside the classroom, and that 92% own a smartphone. So let's first look at the population here. So the population would be the college student market. So that's who Student Monitor is basing the research on. It's the total population that we're looking at for this study. You can think here, who is this research about? If the research is about seniors in America, it's about seniors in America. If it's about doctors in Australia, that's the population. Next, the parameter. Here, we don't really know the parameter. They don't actually give us the parameter here. Often you'll see things like, we assume that this group does X, or prior research has shown that X, something like that. But typically they don't give the parameter. But when they do, it'll say something like that. It'll be referencing the total population and not the specific data that you found in the research study. Next, the sample. So here the sample would be 1,200 students located throughout the United States. The sample is usually just stated outright. The firm did research, the firm used a random sample, things like that. They did a research study on blah. And then lastly, the statistic. So we've got two here. They found that the undergraduates spent an average of 15.1 hours weekly on schoolwork, and 92% of them own a smartphone. So that would be the, ignore where it says sample, that should stay statistic. That would be the statistic here. And statistics will be the result of the current research study being discussed. Typically, it's the thing that's right at the end of the specific quote or prompt or something like that. So a little reminder info, when we're talking about parameters, so the data on the population, if we're talking about counts, so that would be, if we flip a coin 50 times and 25 times it comes up heads, that would be count data. So typically we refer to the mean of count data as mu, or that weird little U with the little dangly thing on it and the little curly thing. Mu, yeah. If it's a proportion, so let's use the same example. If we flip a coin 50 times, 25 times it comes up heads, well, we know that that's half. So that would be a proportion. That would be a percentage between 0 and 1. So when we're referring to that, it's going to be P. When we talk about the sample, well, the sample is going to be, the statistic, if we're referring to count data, it is going to be X bar, or a little X with a little line over it. If we're dealing with proportion here, and I'm not making this up, it's P hat, or P with a little, what was that, like an upside down V over it. Just some little things here. And of course, yeah, I've already gone through this. Count, kind of your counting events. How many hours spent studying, how many times a coin ends up heads, things like that. And then proportion, data that's in percentages. Obviously, in a lot of cases, it would be easy to turn count data to proportion data. It all depends on the research study. All the statistics that you'll be using are all fairly similar. So. Also, we'll talk about sampling variability. So going back to that research study, right? Let's say they did the research study. They found that undergraduates spent an average of 15.1 hours weekly on schoolwork. If we did the research again, we would likely have we would have a new sample. We'd have a completely different group of people. The X bar likely won't come up, the X bar likely won't come up as exactly 15.1 hours. So this is called sampling variability, right? We know that it's going to probably be around this correct number. Remember, we talk about the central limit theorem, the law of large numbers. If we sample a whole bunch of people, the more we sample, the closer it's going to get to the true mean. But we're always going to have some variability. Even flipping a coin, if we did it 1,000,000 times, chances are the odds wouldn't come up exactly 50-50. So yeah, statistics vary in repeated random sampling. Random sampling has a lot of advantages. We'll talk about how it's great to reduce bias, but we always have to consider sampling variability, especially if you're doing small samples. So here's how we test for sampling variability. So first we look at our population and we take a bunch of random samples of the same size from it. We'll collect and calculate the statistic for each sample, so basically our mean. And then we make a histogram of those means. And we're going to be looking at the distribution for shape, center, spread, and outliers. But we would compare it to the regular data, and then we would see if there are any specific outliers there. Obviously, doing a bunch of extra random samples is basically doing new research and can be expensive, but luckily we have software. And it's not something we have to worry about doing. It's just a nice handy little software thing that they do now. So next we talk about bias and variability. So I mentioned a couple of times we need to do multiple samples of the same size. Why do we need to do that? So sampling variability, we need to look at the same size because as sample size goes up, variability goes down. So it's kind of like looking at apples and oranges. If you take a sample of 50 and a sample of 1,000, the sample of 1,000 is always going to be less varied than the sample of 50. So it's not really comparing correct things. Also, variability going down, it basically means the data is going to clump up right around the average. Instead of a nice normal curve, you're going to have one really tall point. So you can see here, so with 5 observations, they're very spread out. You see no pattern. 10 observations, they start kind of forming a little bit of a curve. 20 observations, you've got a nice little normal curve going on there. And now 50 observations, you see it getting taller and taller. At some point, they start clumping her up around the mean so much that the main mean portion becomes very, very tall. So, a little bit on bias and variability. Bias is any problems that alter the center of the distribution from its true value. This could be due to mistakes in the research. This could be because you picked the sampling wrong. This could be because you didn't do the research right. Maybe you made a mistake that, pushed your participants one way or the other. I'll show you a photo in just a little bit, or not a photo, a little drawing. But think of it like shooting an arrow. And maybe you have bad aim, maybe the wind is high, but it keeps on taking it away from the center of the target. So the center of our target is our population mean, the parameter. We want that sample mean to get close to that population mean, but bias is going to pull it away from that bullseye. Next, variability. Well, that's the variation of the spread. It's determined by the sample design and, of course, like we said, the sample size. Much bigger sample size is going to have a lot less variability. Think of it like you're still able to hit the bullseye, but it's pretty random. Sometimes you hit the bullseye and sometimes you accidentally miss the target entirely. So you can see here, low bias and low variance is exactly what we want, right? Everything's right on the bullseye. High bias and low variance, well, all of our arrows are clumped up nicely, but they're way away from the bullseye. High variance, low bias, well, like I said, it hits the bullseye more times than high bias, low variance, but it's still pretty irregular. And high bias, high variance is the worst one of all. Next, we'll talk about margin of error. So margin of error is a numerical measure of that precision, determined by the spread or the variability. Like I said, you're always going to have variability. Even if you take 1 million participants in the study, you're still going to have, plus or minus however percent. We'll talk about margin of error more when we get to confidence intervals in a couple weeks. But for now, this is kind of our quick intro here. You really see this often in things like political polls. It's basically trying to give you a range of accuracy. So I pulled this off the internet. This was a Montana survey for the presidency in 2024. And you can see here Trump, Biden, NA, Jorgensen, and then margin of error plus or minus 4.4% right there. So if you look at Biden's polling data right there, well, his polling data says 43%, but then the margin of error is plus or minus 4.4%. It basically means that Biden's true polling results in this poll of somewhere between 38.6% and 47.4%. So that would be kind of the margin of error. And like I said, this is a very quick intro. We'll definitely get into it more in a week or two. Next, we're going to move on to binomial distribution. This sounds super complicated. Binomial just means 2 possible outcomes. We call those success or failure, right? Either the thing we are looking at did happen or the thing we're looking at didn't happen. If it happens, it's a success. If it doesn't happen, it's a failure. So our probability here, our P, is going to be the same for each observation, right? Tossing a coin, for instance. Even if maybe the coin is not made properly and is weighted one way or the other. If we keep using the same coin over and over again, the odds is always going to be the same. It's going to be completely independent. So P would be the example of success, landing on heads would be the example of success here. So we're looking at P, the probability of landing on heads. We would describe the distribution as B, parentheses, put our n there, and then comma, our probability there. So let's think about this. Is this binomial? Let's look at a hypothetical example of parents that are planning to have 3 children. We want to see whether or not their kids are going to inherit type O blood from their parents. This is independent. Whether or not one child has a specific blood type doesn't determine whether or not another child has a specific blood type. We have a set probability, let's say 0.25%. We have a success and a failure. Success is they have type O blood. Failure is anything else, AB, etc. So yeah, it's pretty binomial. So our distribution here would be B, parentheses 3, comma 0.25. So the sample mean and the standard deviation of binomial distribution. So our mean is going to be n times P, our sample size times the probability of success. And that tells us, on average, how many successes we're going to have. Finding our standard deviation is a little bit more difficult. It's not too bad, though. So our standard deviation is going to be the square root of n times P times 1 minus P. You can think of it like this. Square root of sample size times success rate times failure rate, right? If P is our success rate, well, there's only 2 possible options, 2 possible outcomes. So if we subtract P from 1, that's going to give us our failure rate. So next we'll talk about proportions of binomial distribution. So remember, binomial distribution is going to deal with counts of success and failure rates, right? This is how many of those children, this is how many are going to have type O blood, or something like that. Proportions are going to deal with what percentage of your sample succeeded or failed. So it's always going to be between 0 and 1. So our mean is just going to be P here. It's if our probability is 0.25, then our mean is going to be 0.25, 25%. Our standard deviation is a little similar and a little different here. It's the square root of our successes times our failures divided by our sample size. So that's going to give us our standard deviation for proportions. So let's work through this example. So a survey of 4,972 U.S. students, there we go, aged 12 to 17, revealed that 25% have received mean or hurtful comments online in the past 30 days. You take a random sample of 15 students and ask them whether or not they've received mean or hurtful comments online in the past 30 days. Well, first off, let's see, is it binomial? Well, the probabilities are the same, independent, because if one person receives mean or hurtful comments, that doesn't change the probability of whether or not someone else is going to receive it. We have a success rate. I know it sounds really weird to say getting abused online is a success, but the event happened, so we call those successes. And if all works well, our simple random sample should have the distribution of B 15, 0.25. All right, so let's say that 20% of our sample have received mean comments in the last 30 days. Let's try that out. So looking at it as a binomial distribution, let's find our mean. We do our sample size times our success rate, so 15 times 0.2, we end up with 3. So on average, 3 people in our sample have succeeded or have received abusive comments. Our standard deviation is going to be the square root of, again, our sample size times our success rate times our failure rate. So that equals 2.4. Yeah, because we picked such a small sample size, it doesn't really make as much sense because then we get into the negative numbers here, but yeah, bear with me on this one. Our proportional mean is just p, so it's 0.2. So on average, 20% of our sample has succeeded, as we stated above. And then our standard deviation would be success times failure divided by sample size, and then square root. And that's around 0.1. So again, that doesn't really make as much sense. But yeah, so in that case, that would be how we calculate our mean as binomial as well as proportional. That's it for today. Send me any messages if you have any questions. Beyond that, have a great one, and I'll talk to y'all later.